And well, I hope everybody's doing fine. And today I'd like to present some work that I did at some point to be able to select metabolites in a rather robust and confident manner. So that's also the title, Robust and Confident Predictor Selection in Metabolomics. Let me give you a small introduction to the problem at hand. In untargeted metabolomics, we focus on detection and quantification of all the small molecules in a sample. That would be, I guess, the most broad sense description. And usually this leads to hundreds, maybe more, of signals or putative metabolites. Well, usually not all the metabolites that we measured, they are related to the problem at hand. I'd say that usually it's just a handful of metabolites that are related to the problem that you're studying. And this way we use metabolomics as a discovery tool. But we still need to discover the metabolites that are relevant for us. So from a statistical point of view, what we often like to do is to find the metabolites. And if we want to do classification, we want to find metabolites that are statistically significant, that show us the difference between case control studies. If we want to make a model, we'd like to predict maybe a quantitative trait. Then we need to identify the metabolites that give us the best predictive properties that our model can have. Well, for today, I'd like to focus on the last one, the prediction for of a quantitative response. In that situation, for the quantitative modeling, what do we like to do? Well, we want to identify the metabolites that correlate best to a certain phenotypical trait. And these traits, they can be anything. They can be sensory traits, they can be things like yields, or they can be things like color, all these things. And these metabolites, we would like to identify them that are most predictive, because we would like to use these metabolites as predictive biomarkers, for instance. What could we do if we have identified those? Well, in follow-up research, we could use these metabolites, for instance, in a targeted way. So we don't do untargeted metabolomics, but we just do a targeted analysis. And we can, for instance, use it to predict the quality of a crop. We can indicate whether a process has reached optimal product quality. All these type of things. So in this setting, what are typical goals? Well, first of all, we would like to select metabolites that predict this phenotypical trait the best. Out of the hundreds of signals, metabolites that we have, we'd like to find the ones that are relevant for us. And once we have done that, once we have created a model, we would like to know, well, how well can our model now actually predict this trait? Having a model is one, but it should also be a good model. So that is what we want to do. Well, metabolomics data have a few characteristics that may hinder us slightly from a statistical point of view. Usually we have a low number of samples. We have a small number of objects. Those could be people, plants, animals. Those numbers are typically not too big, but we do have many metabolites. And only the small set are relevant. So we need to select the metabolites, but also if we have a small set of metabolites, we run the risk of selecting what I call spurious key metabolites. We run the risk of selecting metabolites that appear to have predictive properties for the data set that we are investigating right now. But if you were to repeat the experiment, very well be that this set of metabolites is not that predictive for future experiments. How could that happen? Well, if you work with small data sets and small, that can, that's a bit hard to define. I guess it depends a little bit on specific case studies. But if you have a small number of samples, there's a high probability of finding accidental chance correlations. It could be that the metabolites that you find, that they appear to be predictive for your data set at hand, but not really for the bigger picture for all possible samples that you may encounter. So what this calls for is the need for validation of key metabolites. Yeah, we would like to know how well are the metabolites that we select, how good are they in predicting at all. So to summarize, this is maybe our shopping list. What do we need? Well, we need to be able to select variables. We expect a small number of metabolites being important. We also would like to predict, to validate the predictive properties of these metabolites. We want to assess the quality of the model for unknown observations. I think this is really key. If you make a model, then all the samples that you use in the model building process, the model probably can predict it very well. But you want to predict observations that have not been used in the modeling stage. You would like to predict unknown observations, unknown samples, so to say. So that is what we are aiming for. Well, this slide has two equations. Actually, I was in the introduction, it was already said, I was trained as a chemist formerly, but then I moved at some point to statistics and the analysis of chemical data in the most broad sense. But I work a lot with statisticians, and I know that well, when you give a talk with the head of a statistician, it should have some equations. So this is one of two. What we would like to do is to create this particular model. We have a certain response that could be the sensory trait, and later on I will introduce a data set and I will predict some sensory traits, but this will be a sensory trait, and we will try to predict it using a matrix of metabolites. These are all the metabolites that we have measured, and the link between the sensory trait and the metabolites is given by the regression coefficients, the betas, the factor of betas. And then there is, of course, the small errors that we make because our predictions are not always as good as we want. Well, if you want to model this, you could do this with multiple linear regression. I guess that is most straightforward. But remember, we have the problem that the number of metabolites is actually much larger than the number of samples. And in this situation, things like multiple linear regression don't work. So we feel the need for more complicated regression methods. And ridge regression, the lasso, principal component regression, partial least squares, these are all examples of methods that can actually deal with data that have more variables, more metabolites than observations. But with the exception of the lasso, none of these methods do any variable selection. And that is something that we really want. And the lasso, it doesn't really offer any explicit control in the number of metabolites that we select. You always have to wait and see how many you get. So I was thinking maybe we should try something else. Our aim is always for a small number of metabolites, because we would like to use the model maybe in a targeted setting. So we would like to measure only a small number of metabolites later on in future experiments. We would like to have a fast statistical procedure. We don't want to have long computation times, especially for what I have in mind. So I was thinking, let's use stepwise regression. Well, stepwise regression, it is a bit of an ancient method. I'm not sure how old it is, but it's probably from, I don't know, 1960s or even before that. And stepwise regression is very easy method. It's very easily explained. It just starts with an empty model. What does an empty model mean? Well, an empty model it's a model that only has the constant in the model. So it's empty, there are no metabolites in the model. And then in an iterative way, stepwise regression keeps on adding metabolites until the model no longer improves. So it first tries to find a single metabolite that improves the model the best. And then in the next step, in the next iteration, it tries to find a second metabolite that improves the model the best, on and on it basically goes until it's done. Occasionally, stepwise regression, it tries to remove metabolites that are no longer necessary because it has been replaced by a set of other metabolites, and then the model can actually shrink a little bit. Well, the result of stepwise regression is a set of most predictive metabolites for a certain trait. That's what you get. Okay, that may solve the selection problem, but we would also like to validate our model a bit. Well, the typical way to do it, if you have lots and lots of data, is just to cut your data in two parts. You set a part of the data aside as a separate validation set. maybe 1/3, maybe 1/5 of your data. You randomly select it, you use it as a validation set, and then you build your model on the remaining part. And the idea is that the predictions on the validation set will tell you how well the model is doing actually. And if I want to put it in some sort of schematic, this would be it. This is our complete data set. Then we randomly select one part for the model creation and one part for the model testing. Well, there is a big problem with this because, well, I mentioned it a couple of times. Usually our data sets in Metabolomics are not that big. Yeah, so who has data actually to spare? Who has data? Who has the luxury of data not being used in the model creation part? Because we get better models if you use more data in the creation of your models. So this is not really feasible. Well, there's a way out of this. There is this leave one out cross-validation technique, sometimes also called jackknife. How does leave one out cross-validation work? Well, this also is an iterative procedure. So you iteratively leave out one sample at a time. For instance, first you leave out the first sample, like over here in the schematic, it's the one in red. And then you build the model on the remaining part. So on all the samples 2, 3, 4, and so on, all the way to n. Okay, well, you create a model and then you predict the left out observation. In the next iteration, you repeat the procedure, but this time you leave out a different sample. You leave out sample number 2, and then you build a model on observations 1, 3, 4, all the way to n, and all the way till the last one. You make the model, and then you predict number 2. In the third iteration, you probably get the hang of it. You leave out sample number 3, build a model on the remaining ones, and then you ask for a prediction for the left out observation sample number 3. On and on. You repeat this n times so that every sample has been left out at least once. And then the result of this procedure will be 2 things, I would say. First of all, you get n models, because for every observation you have created a model, and you have n predicted values. So for every sample you have a predicted value. Well, what can we do with this? Well, these predicted values, we can use them to assess the predictive quality. There is this quantity called Q squared. This is, by the way, the second equation that I promised you in the presentation. We can calculate Q squared, and Q squared is very much like R squared. And R squared is just a plain explained variance of a linear regression model. But when you calculate it in this way, you calculate it using the leave one out cross-validated predicted values. So you are basically calculating R squared on observations that were not used in the modeling. And high values mean that the model has good predictive properties. And now the nice thing is that Q squared has a maximum of 1. So you automatically can tell that if it is close to 1, say 0.7, 0.8, or even higher, you know that your model is probably doing quite well. If it's less, the model is not doing that great. And if it's really close to 0, or it can even become slightly negative, then your model is not doing that well. So it's a nicely interpretable quantity. It tells you directly how well your model is doing. Well, there is one loose end. Not sure if you noticed it, but when I was discussing stepwise regression, I casually ignored it a little bit, but I said that stepwise regression keeps on adding metabolites until the model no longer improves. So now the question becomes, how do we decide, or how does stepwise regression decide how many metabolites to add? Well, originally the way to do it is with classical F-tests. You have an F-test to see if the addition is significant or not, or if the exclusion is non-significant or significant or not. Well, these F-tests in stepwise regression, they have received some criticisms. If you'd like to read about it, I think they're already in the Wikipedia page on stepwise regression. But there's also another way around it, because we could use its own cross-validation. We could cross-validate the number of metabolites in the stepwise regression model. So given a training set, given the samples, the n-1 samples, we can just run another leave one out cross-validation. It's a cross-validation within a cross-validation. So this is actually like these Russian dolls. Yeah, you've probably seen them maybe. It's like these Russian dolls. You open them up and there's another doll inside. And this is like a cross-validation inside a cross-validation. That's what we call a double cross-validation, and the abbreviation would be LOO2CV. It's a nested cross-validation. It consists of an outer cross-validation and an inner cross-validation. The outer cross-validation, that's the usual cross-validation, like I showed in the schematic. Its purpose is to evaluate the predictive properties of the model, of the selected metabolites. But then there's an inner cross-validation, and that inner cross-validation has the purpose of determining the optimal model complexity. And what's model complexity in this sense? Well, it is just the number of metabolites that you would like to have in your regression model. Yeah? And this inner cross-validation, it is part of the construction of the model. It has not so much anything to do anymore with evaluating predictive properties. Well, I think this slide is one of the benefits that we have for doing online presentations, I guess, because if I were to do this with a live audience in a presenting room, I guess nobody could read it, but I hope it's not possible because everybody's probably looking at their screens. This is a workflow of a double cross-validation. And let me just walk you through it. If we just focus first on the top part in the orange box, in a double cross-validation, what happens is that, well, you enter the double cross-validation over here. And the first thing you do is you're going to split all the observations, all the samples, and I have n samples in my data set, into an n-1 part and a single observation. And so I leave one observation out first. And this single observation that I leave out, it's going over here and it's going down and then it's leaving the screen. So I'll come back to that in the next slide. Yeah. Now, what do we do with these n-1 observations, the n-1 samples? Well, we enter the inner cross-validation. And then in the inner cross-validation, it's like another cross-validation. So we split the n-1 observations in an n-2 part and yet another single observation. So we drop out one observation, we have an n-2 part and yet another single observation. The single observation is waiting over here, and the n-2 observations, well, we use it to create forward stepwise regression model. This time I only restrict to forward selection. I don't want to remove anything else. So we do forward selection, stepwise regression. And this time I just make models with different numbers of metabolites. So I make a stepwise regression model with 1 metabolite, with 2, with 3, with 4, and so on. Once I've done that, I'm going to predict the left out observation. And I'm going to predict it using all the models I made with 1, 2, 3, 4, 5 metabolites. And this part I will repeat for all n-1 observations. Yeah. Okay, let's move to the next slide. Because the next slide holds the bottom part of the flow chart. Once I arrive here, what have I done? Well, for all n-1 samples, I have created a bunch of models using 1, 2, 3, 4 metabolites. And what I now can do using all the predictions that I get from the inner cross-validation, I can calculate the root mean square error of cross-validation. That is just a quantitative measure for how well I can predict something for all the models. And by all models, I mean with 1 metabolite, 2, 3, 4, 5, and so on. And now the idea is that the lowest root mean square error of cross-validation is the optimum. Yeah, that gives us the optimal number of metabolites in the model. So suppose it's 3 or 5 or any number, but suppose it's 4. Yeah, what I'm now going to do is I'm going to create one model using the n-1 observations that entered the inner loop. Yeah, so I'm over here in the global picture, and I'm going to create a model using n-1 observations and the optimal number of metabolites. Say it's 4. Using that model, I am now going to predict the left out observations that I left out in the beginning. Yeah, so over here, I left it out and then I said, well, I'm going to save it. I'm going to come back to it, which is now, and I'm going to predict it using the model that I created at the end of the inner loop of the inner cross-validation loop. I'm going to repeat this for all observations in my data set. And once I have done that, well, I have my n models. I have my n predicted values, and I can maybe start summarizing this procedure. I can, for instance, compute the Q-squared I showed. I can create scatter plots. I can have a look at predicted versus observed scatter plots. Maybe I can detect these outlying observations or other gross errors. And what I can also do, since I have these n models, for each model, I can just see what are the selected metabolites, and I can also count from all the models that I generate how often these metabolites have been selected. And that part gives me some extra information, because it will tell me, these were the important metabolites, but they have also been selected this number of times in all the models that were generated. And that can actually help me decide which metabolites are worthwhile to use maybe in a targeted manner, or just to create a final model. Okay, let's bring in some data. Let's see how this works on an actual data set. Yeah, maybe that will help get rid of any unclarities maybe. Yeah, I'm going to use data on cocoa genotypes. Yeah, this is a study of 76 cocoa genotypes, and the metabolite profiles were determined by many analytical techniques: GCMS, LCMS, GC-TOF-MS, PTRMS, all these things. But I'm just going to stick to the LCMS negative mode for now. And this resulted in 229 reconstructed metabolites. So they are really reconstructed metabolites. So we got rid of all the signals that we don't really need. Yeah? The sensory traits that I will try to predict, they were measured, they were determined by a trained panel. I will just use 3. The original data set was much larger, of course, but it's fruity, spicy, and acidic. And I'm also going to throw in a simulated trait, because I was very curious if my method could also give back the, well, metabolites that are directly responsible. So I just summed metabolites 8, 17, and 199, added 20% white noise, and I called that my simulated trait. First of all, let's use plain stepwise regression. Yeah, this is probably not what you want to do, but let's just use stepwise regression and see how it goes. And remember, stepwise regression is not coupled to any cross-validation. It is just using f-tests for the inclusion or exclusion of metabolites. And as you can see, for the traits, the list of metabolites are being selected, sometimes it's pretty long. For spicy, it's very short, there's only one. Acidic is quite long, and then the simulated trait, it's not that long, but still there are a number of metabolites over there. And I have the feeling that not all metabolites that have been selected are of importance. For instance, if I just take a look at fruity, you can see that this one, metabolite LCMS negative 994, has an R-squared of 48% on its own. And then if you add the second one, the R-squared increase with, 14%. So this number 2 is actually less important. This one increased only by 4, by 3, by 2, 4, 3, 2. You see that the metabolites selected later on in the process, they are not that important. Probably a bit of overfitting, I suspect. For spicy, there's only one, 31%. That's not very promising. Acidic, well, I guess it's the same story. The list is long, but at the end, the explained variance hardly increases. And for the simulated trait, I think it's good news that we see our metabolites back that I put in the simulated trait. And because I put in 20% of white noise, you can also see that some extra metabolites are popping up, but they're probably not that important. What you could do is you could tweak the f-tests, right? You could just say, I'm going to lower the alpha for inclusion, but that becomes a bit subjective, right? I'm not really sure if that's the direction that we want to go. So let me now show the results of stepwise regression coupled to a leave one out double cross-validation. Remember, we will have as many models as observations. Yeah, that is the outer loop. The outer loop is just a leave one out cross-validation. What we can do for all these models, these N models, we can keep track of all selected metabolites. We can just say, well, this one has been selected, this one, and we can also count how often these metabolites were selected. And given these occurrences, we can calculate 5th and 95th percentiles, which is like some sort of 95% confidence interval of the regression coefficients. And now if you look at the outcomes, you can see that the lists are shorter. That's one thing that I really like a lot. And if we take a look at the column occurrence, we can see that LCMS negative 994 has been selected 100 times. Yeah. The second one, 76%, 76% of times, but these other three, 20, 20, 11. So probably these two are just what you want to stick with. The percentiles, they give you information about maybe the sign or the spread in the magnitude of regression coefficient. That's something you can also use. Spicy has 2 selected metabolites, 88% of the times and 12% of the times. That's probably not going to be very promising. Acidic trait, 2 metabolites that are more than 90% of the time selected. This one 50% of the time, this one 40% of the time. And the simulated trait, well, this trait is of course very simplistic in its nature. You can tell that the selected metabolites that I used have been selected in 100% of the cases. But there are also a bunch of others, and I guess that's just because there's 20% white noise on this particular trait. Yeah, and then the model tries to model that as well. Let's go to the model evaluation, yeah, because the Q-squared will tell us how good is the model anyway. Well, if you just take a look at the Q-squared column, you can see that fruity and spicy have relatively low Q-squared values. Spicy is particularly hard to predict, the spicy of cocoa liquor. I can imagine something with that. And fruity is also a bit difficult to predict, 24% explained variance of unknown samples. If you take a look at acidic, that one goes much better, 0.6 Q-squared, and a simulated rate 0.7, which I guess is reasonable if I put 10% of noise in there. Sorry, 20% of noise in there. If you compare it with the R-squared values of stepwise, you can see that stepwise is always a bit overfitting. Yeah, the validated values are always a bit lower. Okay, let's wrap up things. I think this is a very nice, easy method for selecting a small set of metabolites. Yeah, it avoids overfitting, and it also gives you an estimate of prediction accuracy, which is nice. It tells you how good your model is doing. The metabolite counting in this double cross-validation scheme, I'm going to say it adds credibility to metabolites. If the selection frequency is high, yeah, it will help you decide if it's worth follow-up research on it or not. So I think that's definitely a plus. Well, as a last slide, I want to thank my coworkers because lots of people have worked on generating this data. This is a photo of my campus, which I haven't seen in quite a few months now because of the current situations. And if you liked this talk and you would, well, maybe read up on it maybe later on, this is the publication that we wrote on it some years ago. Yeah, okay, thanks. So maybe there are questions. I'm happy to answer any questions that you may have.